Good afternoon, everyone. I'm Nishant Garg. I'm an associate professor at University of Illinois, and I'm very happy to be here. I've been learning a lot. This is a very different kind of conference to the conferences I'm usually go to. I think I'm a minority here in terms of academics. So I'm here to learn from all the industry folks. Some of the conferences I go to, there's very few industry, so it's great to be here. Thanks so much to Mark for the introduction. Thanks so much to my friends at Urbana-Champaign for inviting me and to come out here. Today, so I'm going to talk about particle packing, size and shape of aggregates. But then I've also been kind of hearing the talks yesterday and seeing kind of the people who are out there. I'm going to also make it a little bit broader and not just size and shape and particle analysis. I'm also going to talk a little bit about other things such as accelerated testing for concrete and some of the push for data centers that is now happening in the US. So it's kind of a little bit more wholesome and covers different interests. But before I get started, I'm kind of in the teaching mode right now. I'm just in the middle of a semester. The class I'm teaching has about 110 students. And it's difficult to keep the students engaged because these are young people. They're always on their phones and their computers. So we have to get their attention. So I want to ask you, right, what is the best way to engage young people? It's through memes, right? I'm going to start off with a meme. Okay, so you may have seen this kind of a meme online, and this is a classic case, where your girlfriend or a spouse or a wife is thinking, I bet he's thinking about other women. How can I improve the particle packing of my aggregates, right? So again, if you are female, you can just swap the gender, and your husband is thinking something, and so on, right? So one of the techniques we've been trying to do here is this technique called Raman imaging for particle mapping. Raman spectroscopy was discovered almost 100 years ago by this Indian scientist. He got a Nobel Prize in physics for that. But really to develop this technique took really 100 years to today with the invention of lasers, with the invention of these hyperspectral microscopes, that you can create these very nice images which are very, very information rich, right? Just to give you an example how it works is if this is a piece of rock, you collect spectra at different points. You get this spectra, you split into different components, and then you get a spatial distribution of different things. So for example, if you look at here, so this particular mineral or phase is right over there. In an optical image, it was not visible, but in the hyperspectral image, it is quite easy to see. To give you an example, I'm going to take a material here, which many of you may be familiar with, and maybe, I'm back in the teaching mode, so I'm going to presume you're my students, so I'm going to ask you a quiz. Okay? If you give the right answer, you'll get some points. Can anybody guess what kind of material is this? And I can give you a hint. I can bet that almost all of you, or many of you, have put this material in your mouth at some point. Yeah. Tylenol? It is Excedrin, but Tylenol is also very close. Let's give that gentleman a hand. Okay. Talk to me after class. All right. So you can see the pharmaceutical industry has been doing this, right? You can map aspirin, Tylenol, and caffeine quite nicely. This is a cross-section of a pill, right? You can not only quantify the ingredients, but you can also see the spatial distribution, right? So if they had some problem in quality control, and you're somebody like me, and they put all the caffeine on the right side, you're somebody like me who likes to save money and take half the tablet, I'll just get high on caffeine. I'll not get the Tylenol, right? So we thought, why don't we do the same thing for cement? Why don't we try to map the phase of the cement using the same technique? And that's what we did. So this is the work we did with my first PhD student. We made tiny pills of cement embedded in epoxy, which we're holding in our hands. And what we do with this cement pill is we create this very high resolution Raman image to capture all the phases that are present, right? We compare this with another technique, which is XRD, X-ray diffraction. This is the gold standard for a cement producer. And when you get a very good correlation between two techniques, it's like getting agreement across two different parties, which is very difficult, but it is happening here. We can then start to see individual grains of a phase at very, very high resolution. Right? We can do this for almost all the phases, even down to something like 1% quartz, which is an impurity, right? So at this point, even the cement producers don't have this level of detail and knowledge that we have, okay? And one of the things I tell my students is that they really have become tailors now, because the reason we're able to do this by stitching together many images, right? We take many smaller images and stitch them together to get a large, statistically relevant image so that it has now 250,000 pixels in each image. When you do that at such scale, the quantification makes sense. Okay? All right, time for another quiz. Can anybody identify this phase? Okay, so this is a bit of a tricky question. It's actually not a Raman image. This is an iPhone photo of the night sky taken by my students, right? So you're looking at the stars, just like astronomers look at the stars, we are looking at the stars of cement. Okay? And you can see the scale bar is slightly different. All right. There's other kind of cements, right? Calcium sulfur-aluminate cements, LC3 cements. We are now starting to map all of these via this kind of imaging approach. You can precisely measure how much of these particles are in there and what kind they are. And then we compare them with other techniques to see what kind of agreement we have. And then we can know that, okay, we have some reasonable data. Right? So in this particular case, we are now starting to see the kind of first images of this phase called yeelamite in calcium sulfur-aluminate cements, or you may not know them as type K or expansive cements. This set very, very fast. In like few minutes, you get very high strength, what you would get in a few days. And it's coming from that phase called yeelamite, which can now see individual grains at this level. Okay. So that's particle analysis. Let's talk a little bit about now size and shape, right? We all talk about size, but sometimes I feel like shape doesn't get talked about a lot. So I'm going to show you here a picture of one of my students. You may also have seen him online. This student is always distracted, right? And I said, don't get distracted. Don't think about, when you're doing the mix design, adding more cement to get more strength or adding more water to get your workability. Think about your gradation, right? Because that's the ignored girlfriend, that my student has. And it's just chasing the other girlfriend, which is going to be expensive, right? And it's going to ruin the existing relationship, okay? So let's see if we can teach the student how to pay focus or pay attention to what he already has. So we came up with this metric called the particle packing factor. And the way we went about this is very simple. We said, okay, let's take all the ingredients in concrete, starting from aggregate to all the binders, right? Cement, fly ash, slag. Let's measure their particle size distributions. Let's look at the theoretical packing curve according to the Anderson and Anderson model, which says if you have particles in that packing curve, that's the best packing. Okay. Then measure the packing of our system and simply subtract the system between the ideal case and our case, and the difference, we quantify it, and we call that difference simply PPF, right? Particle packing factor. And turns out this particle packing factor is very highly correlated to many properties ranging from strength to workability, right? So we see some selected results here of how this works. Essentially, we made a bunch of UHPC mixes. So this was a project where we wanted to make ultra-high performance concrete, which is 4 times stronger than your general concrete. So if your general concrete is 4,000 PSI, this could be 18,000 PSI, 20,000 PSI. And there's a huge, I think, potential for this material. You can now replace steel. You can have concrete without any rebar with this material, right? So we did this work with IDOT. The DOT was very interested in taking it forward. We start to plot the correlation between the particle packing factor and the flow that you get per unit of the high-range water reducer. Okay? Initially, when I look at this data, I'm talking to a student like, this data is junk, right? There's no correlation here. But then we say, okay, let's go back and think about what is happening. We really realized that looking at all of these mixes, there is no correlation. But if we break them down, depending on the silica fume content, we decide 3 zones based on the dosage. It turns out there's actually 3 different zones where the correlation actually works, right? So across mixes, the data looks junk, but if you look at specific set of mixes based on the silica fume content, there's actually very nice correlations, right? So sometimes it looks like bad news, but you have to do a little bit more digging. What is happening is that the higher PPF value, you have now more free water, which allows better lubrication, better packing. Okay. Moving forward, we also take this data for strength. Again, we measure strength at all different ages. We came up with this kind of very interesting charts of how the strength is varying depending on the 3 things here. 3 things here are the silica fume, slag, and ultrafine fly ash. By changing these 3 binders, how the strength changes, we're able to see that. But then really what is more interesting here is if we plot the strength versus the packing factor, again, you can see almost a linear increase in strength as you get to better packing, right? So really optimizing the packing can give a meaningful difference in strength. Again, this is in megapascal. When I convert it to PSI, I can do the multiplication by 145, but these are large numbers. Finally, the third thing is the durability, which we measure with porosity. And there also, we see a very nice correlation between the open porosity and the strength. So you get to lower porosity values and very, very high strength. So again, your typical concrete is around 30 megapascal. Your ultra high performance, you can go to 120 megapascal and has very low porosity, right? So very high durability, very long service life for your structures. And then if there's no steel in it, there's very less risk of corrosion. Okay. And again, you do this correlations, step by step, and you can see this. I was in China, I think, last year, and attended a conference on UHPC. They're building bridges out of UHPC. They're making UHPC panels in precast sites, take them to trucks to a bridge, making it like a Lego structure. It's really fascinating. And you can take your UHPC, combine that with steel beams. You can have composite panels which are hollow, so you have much lighter weight, and the span of the bridge increases, and you don't need much more, let's say, piers. You can have much more traffic beneath the bridge. This is really, I think, the material of the future. But again, it relies that we must pay attention to particle packing. Okay. Then the third thing we did here was looking at shape, right? So I had this project where I did not have a lot of money, and I said, okay, we have this $200 microscope in our basement, nobody's using it, and the student was new, and I was like, okay, why don't you go ahead and use it and see what you can do with it. So I spent 1 year with an undergrad. They took a lot of images for sand, fine aggregate, and they came up with this very neat thing called the particle shape metric, where you combine 3 different things: the circularity, the roundness, and aspect ratio, and you can then have this very simple parameter which basically correlates with many different things, right? Whether it is packing coefficient, which we get from helium picnometry, or the yield stress, which is measure of the rheology, or the strength and the open porosity, right? Again, we took a bunch of sands, imaged hundreds of particles, and just look at their shape, right? And all their size, we kept them as constant. We can see the shape alone has a huge difference, right? And this is what I'm really, I think I want to maybe take a pause here and mention that what I'm really happy that this is now actually happening on the industry scale, right? I see companies like Urbana, they're coming up with these kind of imaging methods to measure aggregate size and shape in the field. I think which is going to be really interesting. So every time I see things going from the lab to the field, I think that's a big win. Okay, then what can we do? Can we do size and shape of the clinker of the cement phases? We have also done that. This is again on the very finer scale, the micron scale. Again, we take this very high resolution images, and you can see that now you can see the individual size and shape of even this micron size particles, right? And by this, what we can do is for your cement, instead of having one particle size distribution for a powder, you can have the phase-specific PhDs, right? Because we know that powder is made of 10 different powders, right? So you can get a PhD for quartz and a PhD for alite. We hear all these issues with type 1L cements. Well, one of my hypotheses is that the limestone inside those type 1L cements, its fineness is varying. Even though you could have 2 cements with 10% limestone, but the limestone fineness is changing depending on how they are grinded, right? Either it's intergrinding or separate grinding, and so on. And this is why we see some of those variability issues, right? Anyway, that's my working hypothesis. And then we can get all sorts of other metrics such as size and shape of these individual phases, which turns to match out, right? Your B-light tends to be round, and we see that. And this work came out on the cover of JPCC, so we were very proud of that. My student went and did some nice graphics for this. But really, again, what's the value of this, right? The value here is that if you think about all of the cement powder individual particles like M&Ms, you can think that either they're all equal size, equal shape, but in reality, they're all different sizes and shapes and randomly oriented. And we came up with this very simple empirical coefficient called the composition size quotient, where we combine the composition of the cement and the size into a single parameter. And this parameter can then predict the 3-day cumulative heat of that cement, which is a good predictor of the overall hydration and the performance of that cement, right? Again, just looking at the size and shape and the composition initially. All right, then the fourth part of this talk, I want to talk about accelerated testing. And again, before I talk, maybe just do a little bit of a zoom out. If you think about from a point of a PhD student, right? If you remember this scene from Inception, right? It'd be much better to do a PhD somewhere else because it takes very long on Earth, right? If you think about why do I care so much about time? People say time is money, but I want to make an argument that time is actually greater than money. And why is that? Well, let's think about money. It's essentially capital and materials and labor in principle can be scaled up, right? If you think about time, that is actually a much more scarce resource. Why do you say that? Talk about money, our universe, the universe we all share, has turn raised to about 22 stars, right? Which have, many of them have systems like ours, the solar system, and immense amount of mineral resources and metals which can be mined. The only question is how do we mine them and when do we mine them, right? So I think the automation in advances in automation and robotics will lead to a huge reduction in the cost of accessing these resources. So over the next 1,000 years, we were talking about yesterday, making projections. So I'm going to make a projection a bit long term, like over the 1,000 years, we will have the ability to mine these resources. And of course, we may need to build a few Dyson spheres on the way, but it can be done. However, time is still scarce, right? We're still limited to living to 100 years. There's no elves inside. Maybe there's some elves in this room. Please come talk to me after the class and share your secrets. And there's no time machine yet, right? And there's big fundamental limits to if that can be done. So, in summary, with all that text, robotics and automation is going to continue to accelerate, and we will free up, reduce the money it takes to get those resources, have a lot of abundance, and the elves are still gonna be not in sight, so we have to be really careful with our time. Okay. All right. On that note, can we accelerate the testing and the mixed design and the QC of concrete because we know we are so limited on time, right? When I see that, okay, still in 2025, we're waiting 1 month to get the 28-day strength. We're waiting several months to do durability testing. Can we reduce that to a few days? Can we reduce that to a few minutes, right? So that's the question we started to ask a couple of years ago, and we started to look at, the first thing was the reactivity of supplementary cementitious materials, such as fly ash, slag, natural pozzolans, and things such as calcined clays. So this was the work done by a team of students here. We came up with a very kind of a neat, low-cost method using cameras to detect concentrations of aluminum and silicon in these liquids, which would typically require an expensive piece of equipment like an ICP, which is like a few $100K, and this is all done with like a $50 camera, right? So if you look at reactivity tests, and without going too much in detail, there's the strength activity index test, takes about 28 days. I call it the tortoise. There was the R3 test developed 10 years ago. It's a little bit faster, can be done in a week. And then the test that my lab has developed, we call it the UR2 test. I'm still kind of thinking about what animal to call it, but we're going with this fast-running cheetah. And there's many tests, there's many animals in the jungle, right? And if you want to interest, you can read this paper. But really, I want to talk briefly about the newer test that we have. Essentially, what we came up with this idea that if something doesn't dissolve, it's not reactive. And then it's a question of what are the right conditions at which you should dissolve it. So figure out, having the right amount of NaOH concentration and the temperature. And when you dissolve it, you can get the right concentrations, which then map to long-term reactivity. Okay. And then you got aluminum and silicon, how are you going to measure it? Well, you can use an expensive ICP, like 300K, or you can simply take a picture of it, right? Calibrate the color to the concentration, and you have a very low-cost sensor to measure these concentrations, which is at the ppm to ppb level, okay, parts per billion. We come up with this index, done in 5 minutes, and turns out I'm going to show some results here with one of the samples here. This is calcined clays. It's an emerging SCM in several parts of the world. There's some few plants come up in Africa because there's a shortage of limestone over there. By testing more than 100 calcined clays, we actually have a very nice correlation between the 5-minute and the 7-day method. And if you compare the 5-minute method with the 28-day, there also we see a very nice correlation. The next step is now to test this material in fly ashes, natural pozzolans. We are seeing promising results on those materials, so that can be universal for all SCMs. But for that, maybe we have to wait until next year to see how the results are. And the long-term aspiration is to build an automated sort of a benchtop version and an inline version so that this test can be in a fully automated way. So nobody has to do that wet chemistry, and you just drop a 1 gram of your SCM. In 5 minutes, it tells you what's the quality of it. And for a producer, like an SCM producer, they can do real-time quality control for their any kind of operation, whether drying, grinding, calcining, and make a very consistent product for the end user, which will be a concrete producer. The other thing we have been also looking at the durability of concrete, right? We want to make concrete which lasts for a long time and doesn't suffer from failure and cracking and so on. So we started looking at sorptivity test, and we developed this method using, again, low-cost cameras. Using computer vision, we're able to track the intake of water in concrete. Essentially, if you consider concrete, the 1585 is the standard test where you measure the weight change as it absorbs water. We said, why don't we do it with cameras? Because we know concrete is really like a sponge. It slowly sucks in water, right, if you expose it from the bottom. And if you can quantify it using computer vision, we can actually then start to predict sorptivity. And a student here was a bit creative, so he made Illinois logo mortars and see the water going into those shaped cubes. And we can see for paste through concrete, we are now able to predict sorptivity reasonably well. This particular work, all the code, everything is available online, so you can find and download and run on your own. Only thing you need to do is buy these $30 cameras, and everything else is available for free. Finally, I want to talk a little bit about some of the work we're doing with some of the big tech companies in helping build their data centers and specifically design the concrete for those mixes. So here's one example, the latest data center from Meta in Minnesota. This is going to be coming up online in next year. It's about 700,000 square feet, so really, really massive structure. The AI Optimix is developed jointly by Meta, Amrise, and my lab at University of Illinois. And you can now find online all the kind of details. There's several news releases. We're still writing the technical paper on this, so next year you'll have a more technical paper, but if you want to read for a general audience, you can find these links. But the whole idea here is you can essentially use AI to build data centers to build more AI. Okay, so kind of like a very circular AI thing. So what we do here is we take all the materials from that specific site, right? Because we know the materials quality can change from site to site. We bring it to our lab, we design concrete mixes, test them, feed them to the open source AI model that Meta has developed. We get the results, feed them back into our lab, do some optimizations. It's kind of a human and AI mixed optimization. And ultimately, the AI starts to now generate mixes which are actually quite interesting. For example, in one of the cases here, for an application, if you consider this Pareto frontier of strength versus global warming potential in terms of CO2 footprint, the AI-generated mixes can start to even exceed the performance of industry mixes depending on what you're measuring. So in this case, we care about strength in GWP. You generally want to move further and further into this direction where you have lower GWP and higher strength. That's one thing, right? You can generate mixes based on what your requirements are. The second thing is you can now forecast and predict the strength gain, right? So you can say that, okay, I have this mix, predict what the strength gain is going to be. Again, in this one example, this is what is the AI mix predicts. It's like forecasting weather, right? For forecasting weather today, the AI is much better than human forecasters, right? It can predict much better than what the humans can. It's the same thing we want to do for concrete that, okay, for the next 28 days, this is how the strength will look like. This is the error. And then green is what is actually measured. Right? Again, but I want to be very clear that this is very early preliminary data. It's built on a relatively small data set of a few hundred mixes, which was done at our lab. In the future, as the data set becomes bigger and we get more and more variety of different things, this will only get stronger. Right? And again, here also I want to maybe point out, right, there's several companies, right? Companies like Geotech here, they're building this AI-based platform which can also do this kind of a similar thing, right? I would say one difference here is this is the direction here we're taking is an open source approach, so anybody can use it for an academic purpose, or if there's a industry person who wants to adopt and play with their data, that's something can be done. But again, there's a lot of work that still needs to be done, but the early results are quite promising. Okay. So again, to summarize in a meme, right, what do you want to do? Do you want to maximize performance or minimize CO2 footprint? And sometimes this is a kind of a stressful decision, right, because you add more SEMs and your early performance suffers, your strength goes down, and your other issues start to be. But if you optimize using AI, you can actually have both, right? So this is the future, I think we are aspiring for. And it is possible. It is definitely possible. We just need to have clearly defined specs of what kind of performance we're looking for, and we can have it. Okay. In terms of outlook, there's a bunch of papers that have come out of the past few years from my lab. Again, all of them are available online. You should be able to access them. If you have any problem, you can email me or one of my students, and we can share those with you. In terms of summarizing the outlook here, the particle analysis, Raman imaging is a powerful tool for phase identification. Size and shape of all the binders and the aggregates are very important levers to optimize the concrete performance. The accelerated testing is another thing I'm very passionate about, and here some of the tests we have for reactivity and sorptivity can be very helpful in speeding up that initial mix design, right? There's a lot of new materials also coming in the market. If you're going to spend years to validate them, so much money and time is lost. And finally, data centers is going to continue to grow, both in terms of their number and size. Right? There's some projections that even at some point when the human population stabilizes, I really hope it doesn't, with all that plans to colonize different planets and so on. I think it will continue to exponentially grow. But at some case, if it were to stabilize, the only thing we'll be building is still data centers, right? Because our demand for data demand for data and computation is going to only increase. So there is a lot of opportunity to make significant gains in speed, performance, cost, and sustainability, right? 4 levers, very complicated to do it for a single human, but AI can help. Okay, so with that, I want to thank all my students who really helped me do all the things mentioned here. I want to thank my group. Thank you to all, and if anybody wants a copy of these slides, I've put a PDF under this QR code. You're welcome to download it, and with that, I'm happy to take questions.
Yeah, part of your testing, did you take into account different mineralogies, like, for instance, limestone? Typically, you'll get additional lime into your mixes. And then also talk about how all through your testing did you look at, like, the sand particles and, your sand equivalencies and compensate for clays that may be associated with those particles?
Right. So I guess there's 2 questions here. The first one, when you say take into account the limestone, are you talking about the limestone in the type 1L? Cement or?
No, specifically to the aggregate, right? So you're gaining some additional limestone if it's on the a decant on your crushed limestone, depending on the mineralogy of your aggregate.
Oh, I see. Okay, so this is for the size and the shape work, right? So for that work, we did not vary the mineralogy, right? We just stick to same kind of mineralogy, but only play with the size and shape. Okay. In the future, yes, we want to then take it next step forward. We start playing with the mineralogy as well, whether it's limestone, granite, or different kinds.
Two questions. On that reactivity test, are you at a working standard?
No, not yet. So I think my goal here is that we have tested this fully and shown the data on calcined clays. I would like to do this on fly ashes, natural pozzolans, fully vet the method, and then maybe go to ASTM and get like a standard. And then at that point would be a good step to move forward, because I don't want to spend all the time to get a standard out, but then the method doesn't work on other materials.
In the bigger picture with the civil engineering profession, are you and your colleagues stressing for the next generation of engineers that for concrete technology and materials, that the whole material mix is going to change, that the availability of higher quality materials will not be the same as it was in the past, and that engineers will have to be more creative in how they approach mixed designs and how they propose them to agencies and customers?
Yeah, I think that's a very, very good question. I think there's 2 sides to that, right? The short answer is generally yes, because now the complexity of the concrete is only going to increase, right? We have much more different kind of SCMs, all these blended cements, right? We have the type 1L, but then we'll have type 1P, type 1T on the horizon. So for a concrete mix designer and the next generation of students, it is going to be much harder as opposed to 30 years ago when you have very less ingredients. Same on the admixture side. There's so many admixtures on the market, right? So it will get harder, right? The second part, and then we have to educate and train them, and that's what we're trying to do. But the second part is with tools, newer tools, whether it's tools such as advanced characterization methods, advanced microscopes, or advanced low-cost sensors, and AI, it will also get then easier to handle that complexity, right? So this kind of, things are getting difficult, but our tools are also getting more sophisticated. So it's just that kind of future.
Yes. Last question, then we'll move on. Thanks, Nishant. That was great. Question about the phase quantification or particle sizing. Do you think that within the next 5 years, or say 10 years maybe, that we can have hyperspectral or Raman spectroscopy at the edge, like at production sites, so that operators can understand the phases as they're batching, and they can make adjustments or send, call up their suppliers and say something's wrong here?
Yeah, I think it's a really, really nice question. And I think this is like the long-term vision, right? So I can tell you in 2018, like 7 years ago when I was hired at the university, somebody asked me that question. And I said, yeah, in 10 years, we'll have that, right? So 7 years are gone, okay? I think, we are optimistic that it's going to happen, but it really takes some time. The bottleneck is there, for the Raman imaging work. That sensor is pretty expensive, right? That equipment is like $300K equipment. So somebody has to really, really downscale that, make a cheaper version of that, I don't know, 10K, 20K, to bring it to a concrete plant, right? And but it can be done. And that's something I really would like to build, but I don't want to give a time frame because, time frames are tough. Like the first adopters should be really cement producers, right? Cement producers right now using X-ray diffraction. So they want to move on to Raman imaging and use it as a complementary tool. The other adopters I want to be the consultants, right? The forensic investigators. They still use optical microscopy for petrography, right? And I talk to them, hey, let's use SEM and Raman. They're like, no, the optical system is just good. And we have to convince those guys. So yeah, forensic experts, cement producers are the first target, then concrete producers are after, and then aggregate producers are after, right? So we have to wait. But it's going to happen.
Okay, thank you. Thank you very much, Professor.